Alright, so hopefully I could do this video pretty smoothly, and there's not gonna be any problems. So I'm gonna talk about calculus because I was so much into the trig and stuff. So let me just go straight into calculus. So what calculus is about is the reason behind calculus is to find the slopes of lines and to master lines. So we have a line like this, da da, and there's y and x axis. And what happens is that we know a slope of a line equals the change of the y over the change of the x. And you don't have to worry about y and x, just say the y axis and the x axis. And whenever you see change, it means that the final minus the initial, y2 minus y1. And final minus initial is actually the correct way to say it. So if I say, okay, this is 1, 2, 3, 4, and 1, 2, and I say, okay, well, what's the slope from here to here? That'll be the final y. So this is the final point. It starts here, and it moves up here. So the final point's 2, and the initial point's 1, over the final x is 3, and the initial x is 1. So you get a slope of 1 over 2. And so right now, the y and x doesn't really have any units. It's just y of x, right? But let's say that instead of y and x, we have the position and time. So you have position over time. So, and when we do position over time, we're going to say that the position is miles, and time's going to be hours. So you have miles per hour. So, we could change these up as much as you want. Like, let's say that it's Thanksgiving Day, and it's Thanksgiving Day, and we want to cook chickens. So we have the number of chickens, and then you have the amount of time it takes to cook the amount of time to cook all those chickens. So let's say that. So in this graph, we're just saying that, oh my gosh, you can make one chicken for every 2 hours. So it's gonna be chickens per hour. What this says is one chicken every 2 hours. And this could go for anything as long as these depend on each other. So if this time has a relationship with this, or let's say that we have I don't know, let's say that this is not true, of course. I'm just making up these numbers. Let's say that I have the number of chickens with the position of my car, because for whatever reason, whenever I move my car, a chicken gets made. Just really silly, but I just want to show you that what actually these things are, just as a relationship with one another. So this means that, oh my god, so that means let's say the position is in miles, and this is chickens. So oh my god, so that means that one chicken is made every 2 miles. So you have chickens per mile. And basically what you're doing is you're just finding the slope over and over again. You find like a common idea of, oh, how many chickens are for this many miles, or it's the wording, it doesn't really matter. Like the the y and x axis, do not get that confused. Do not get freaked out because it's not y and x. Just imagine it as a relationship. In a regular graph, you have a relationship of the y to the x. So y changes with the change of x. Vice versa. X changes with the change of y. Dependent, independent variables type thing. So what calculus does is that you find like the smallest slope possible. So in regular, let's say this is 1, 2, 1, 2. Well, instead of doing like, oh, this is, per hour, we could do per infinitely small hour. So per like millisecond. Da 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 da. So that means you could get the exact amount at any point right there. So this is what you're called when it hits 1 point only, because the slope is so small that it only hits 1 point on the graph. This is called the tangent line. So when it only hits 1 point, that's the tangent line. Normally, until this point, we've been only working with secant lines, which is it hits 2 or more points. Bop bop, that's the secant line. And even if you try to draw, even this one, when I try to draw this, I'm hitting infinitely many points. I'm hitting so many points right here that it's a secant line. Like it's almost impossible to draw a tangent line. But the question is like how? Well then, how would you create a tangent line? And before you really get into like creating tangent lines in calculus, you have to understand exactly what a limit is. And the limit is approaching a number. It's approaching. So let's say that I have this graph, and I have the graph is y squared equals x. So it looks like this. Boom, y squared equals x. Oh wait, sorry, this is a little off. I meant y equals x squared. You could just ignore that. Y equals x squared, which means that for every y, there's 2 x's. So let's say that I want to find when, I don't know, x is 2. Boom, x is 2. Blah, blah, blah. We say, well, the limit, what you're actually doing in your head is you're doing the limit as x goes to 2. So when x goes to 2 on both sides, you like look at it like, okay, well, what's the y? So when x is 2, you get y equals square root of 2, which is right here. Blah, blah, blah. Okay. Now, what if that didn't exist? For example, what if you have a graph, same graph, but instead at 2 we have a hole. But hole. You actually like physically there's nothing there. There's nothing there. And like in all honesty, in any type of math before calculus, you just say the answer does not exist at that point. It does not exist. But we're gonna try and go around that idea by saying, as we approach from both sides, these are arrows. As we approach from both sides, there you go. As you approach from both sides, what should it be? It's an approximation. So so we say, okay, well, we're gonna go from this side first. We're gonna do the left side. So we're gonna say the limit as x is approaches 2. On the left side, you put a 2 after you put a negative after the 2 to say the left side. We have, remember, there's y equals x squared. We're gonna try and estimate this by putting a number, and there's no equal sign right here. Sorry. We try to estimate this by putting a number that is so close to the left side that you could pretty much say that's the point where it hits it, in a way that you say, okay, well, let y equal we're gonna do y equals 1.999 squared. Okay, and when you actually set up the limit, it normally looks like this. and then you plug in your 1.9999. There is no y equals x y equals, just because they pretty much assume that you already know that it's y equals. So there's no y equals when you actually do it. But what happens is, so you're gonna plug in this number 1.99 squared. You're gonna come out with a number like, let's see, and I guess I'm gonna multiply it again because I don't know how to square in this. 3.996. So we're gonna get, so this equals 3.996, and this is the limit as x is approached on the left side. Boom. Well, how about this side? How about we do this side? Boom, boom. What would that be? So if we do this side, we're going to do limit as x is approached to on the right side, x squared. We're going to say, okay, well, this is going to be 2.0001 squared. And we're going to say, okay, well, 2.001 times 2.001, 4.004. So we say it's about 4.004. And this is the limit as x is approached on the right side. And yeah, you can look at this and be like, well, it's obviously 2. But things get more complicated, but I'm just simplifying it right now. So, what we get from conclusion of this is that we could say, okay, if on the left side it's 3.996 and on the right side it's 4.004, we're just going to say the limit as x approaches 2 is approximately 4, because it would just make sense. So let's do a more complicated one where it's not as easy to see. So we're going to do a different limit, and we're going to say, okay, well, what about the limit as x approaches 0, and we have x over the square root x plus 1 minus 1. So if you try to plug in the normal way, you say, okay, 0 over square root of 0 plus 1 minus 1. You get 0 over 0. And of course, this does not exist. But we're going to do limits to try and find the number that should be there if it did exist. So we're going to say, okay, well, we're going to approach this on the left side. So we're going to say limit as x is approached on the left side to 0. So for x on the top, we're going to say, okay, well, we're going to do negative 0.999 over square root of negative 0.999, because this is so close to 1. Plus 1 square root minus 1. Well, this is not exactly really close. I think I'm going to get a lot closer just by, instead of doing negative 0.999, I'll do negative 0.01 or 0.0001. I think that's a lot closer number, just so we can make sure that we have all our stuff right. Remember, this is not negative. This is 0 on the left side. So, yeah, 0.99 wasn't as close to 0. I think this is a lot easier. And if we plug this in, we get about we get limit, as x approaches 0 on the left side to be 1.999995 or something like that. Boom. Well, let's try the right side. Right? Approaches 0 on the right side. We're going to put in 0.0001 over square root of 0.0001 plus 1 minus 1. And you get about 2.00005. So, based off of this, you can say that the limit as the limit of f of x, because this is the standard way to say it, as x approaches infinity, x 0 is about 2. And this is a legit answer. We're really close to 2 on both sides. So yeah, this is basically what a limit is. You're taking stuff from both sides. And of course, the first step to every limit is plug it into the equation to make sure it does not exist. Because if it exists, then you don't have to do the limit, because you can just get the answer. So you should probably plug it in first, and then you go through the process of left and right bounds. So I think I'm gonna stop right there. So the scientist, stop right there. So the scientist, he basically came up with a formal definition of a limit. So he came up with the definition of what a limit actually is, and it goes into like so this is probably the hardest part of Calc 1, is just understanding this. But he goes on to the epsilon delta definition of a limit, and I'll keep that for the next video. But I just want to make sure this video goes over well and see how what you think of it and such. So yeah, I'll talk to you later.